Okay. All right, so a screen lies over a garden in the shape of half of a cylinder. Okay, radius equal to 10 feet and length 20 feet. Axis of the cylinder on the x-axis. Okay, there's a lot of information there. So here's the x-axis. So that x-axis is the axis of the cylinder, and we're looking at half of the cylinder. The screen lies over the garden, not under it, right? So I claim that what we've got here is a screen kind of like this, and it goes out like that, a certain distance. And let me go just a little further for artistic reasons. Oh, that's, gosh, okay. Cool? Okay. All right. Let's see here. So radius is 10. Okay, so that's 10. And this is 20. Here. Okay. All right, so I that should have been over a little further because that needs to be parallel. So that's sorry about the awkwardness over here. It's a little Picasso on this side of the picture. Okay, so let's see now. Locusts trap themselves in okay, rate of F per square foot per day. So look, we've got some function. All right, we'll worry about what we're doing with it in a minute. Okay, so now, but X is the horizontal distance from one edge of the garden. Well, good, that's the way I set it up, right? I mean, I've got, so, the X coordinate means the distance from that edge of the garden. And Z is the height above ground level. Well, good, that's, again, the way I have it set up, so that's good. Okay, so we want to use this notion of scalar surface integral to write down an expression, total rate, that locusts trap themselves in the screen. All right, so the total rate, so in other words, locusts per day, I claim, if you think about it, we're just going to add up over every little piece of the screen. Right, on that little piece of screen, I need to take the area of that and multiply by the rate per unit area. And the rate per unit area is given. F per square foot per day. That's F per day, a rate, times a unit of area, square feet. So we're going to have F per square foot, let me say, per day, and I'm going to multiply that by ds square feet, and the units all together adds up to, well, we have a double integral of f ds, and the units are, the number of locusts per day. That makes sense? So the units all kind of work out. So this is what we're going to calculate. Okay, so, right, so how do you calculate this surface integral? Well, we parameterize the surface, and this is where the hint kicks in. The hint says we want to parameterize using the angle theta measured at the x-axis from the top of the screen to the point in question. So, for example, if I'm looking at that point, right, I'm going to look at that angle theta. Is that cool? And I claim if I know that angle theta and if I know the x-coordinate, if you tell me where the x-coordinate is and then how much angle to go up, then that tells you exactly where you are on the screen. Is that all right? So what I have to do now is figure out how to write, how can I write x, y, and z, x, y, and z in terms of, I want to write all three of these coordinates in terms of x and theta. Well, good news, x is x. And y and z, I claim I can write both in terms of theta. So y, for example, is just going to be 10 cosine theta. And z is 10 sine theta. Right? Is everybody good with that? Now, there's something slightly awkward about this. I've parameterized, I've got a function whose output coordinates are x, y, and z, and then x is also one of the input coordinates, and that's not cool. Let me just scratch that off and just say, u, just to be different. So what I've got here is this is a parameterization that gives you position as functions of u and theta. Okay. All right. So, all right, now it's just a matter of calculating. Let's compute what ds is. Remember, ds is computed in terms of capital N. Capital N is computed in terms of the derivatives of this parameterization. So I've got to write down first what is xu and what is x theta. So xu, all right, well, let's see, here's x. xu, the partials of this with respect to u, that's just 1, 0, 0. That's really easy. Whoops. 1, 0, 0. Okay, x theta, I've got to compute the partials of this parameterization with respect to theta, and that's 0, negative 10 sine theta, and 10 cosine theta. Then n is the cross product of these things. So, okay, that's, I didn't write them down in a way that's going to make them easy to compute the cross product of. But let's see here. So, let's see. Okay, so the 0, negative 10 cosine theta, and negative 10 sine theta. Is that cool? That's just the cross product of these two things. Is everybody good? Okay. All right, so then, of course, I need to compute the length of n. And lucky break, look at this. Sine and cosine, the length of this is just 10. Okay. So that's easy. Okay, so that means that I can rewrite my rate, double integral f ds. I can rewrite that as just double integral f, which of course I have to write in terms of the parameterization, and then times 10, that's my length of n, that's my stretching factor, and then du d theta. And all I have to do now is figure out, well, what's the range of values of u and theta? Well, lucky break, u, namely x, just goes from 0 to 20. Because u is x. And theta, well, theta goes from 0 to pi. That's 0 to pi. And f, let's see, f is this function. Okay, let me do that one last thing. F is, well, let me squeeze this in up here. F is x plus z. But in terms of the parameterization, x plus z is, well, there's x, there's z. It's u plus 10 sine theta. X plus y. All right. So that is your integrand that goes here, and that's the integral you compute.
The order doesn't matter, right? Du, d theta.
Yeah, that's right. This order doesn't matter. In this case, you could do the du integral on the outside if you want, because the range of values are constants. In other words, you have a rectangular domain in the parameter space. So yeah, in u theta space, the domains are rectangular.
Does it ever matter? I mean, if we can change the limits, does the order ever matter?
What? Oh, will it? You mean will it change the value of the integral itself? Yeah, and there are some weirdo cases when you have highly non-continuous weird functions where it does make a difference. So what we have to do, all we have to do is assert that this function is continuous. And in the case when your integrand is continuous and you have a bounded set of domains, there's no problem. But when you relax those constraints, yeah, weird stuff can happen. But Math 103 will not discuss any of that. Yeah. Right. Okay. Okay. Is everybody happy with this problem? Any questions? All right. Good deal. Kill the recording.